Chapter 20, Many Electron Atoms. Section 20.3, The Wave Functions of the Electrons in Atom. There is a systematic way of constructing an anti-symmetric wave function of two or more electrons. That is to use a determinant. Because when we switch two rows or two columns of a determinant, the sign of its value changes. Here's an example. We can use this wave function to describe a two-electron system. The wave function of two electrons, 1, 2, can be expressed as 1 over the square root of 2 factorial times a determinant. In this determinant, electron 1 occupies the first row, electron 2 occupies the second row, and we have phi 1 in the first column, phi 2 in the second column. Phi 1 and phi 2 must be different. We can expand this determinant. We get phi 1 of 1, phi 2 of 2 minus phi 1 of 2 times phi 2 of 1. And this is anti-symmetric, because if we switch 1 and 2, we will switch the sign of the determinant. Phi 1 and phi 2 must be different. They are normalized, they are orthogonal to each other. So here, this is what it means to be normalized. The integral of phi 1 squared d tau is always 1. The integral of phi 2 d tau is always 1. Phi 1 and phi 2 are orthogonal to each other. That means the integral of psi 1 star times phi 2 is 0. The integral of phi 2 star times phi 1 equals 0. Over here we have 1 over the square root of 2 factorial. This is just to normalize this wave function. We have a 3 by 3 determinant. We need to have 1 over the square root of 3 factorial in the front of the determinant to normalize the wave function. For the helium atom, we may propose phi 1 to be the normalization factor n times an exponential function e to the power of negative zeta r times alpha. Phi 2 is the same as phi 1, except the spin is beta. Again, this uppercase N is to normalize phi 1 and phi 2. The physical meaning of the 2 by 2 determinant is this. The two 1s electrons, electron 1 and electron 2, we know they have alpha spin and beta spin, but we cannot tell which electron is alpha, which is beta. Both electrons are both alpha and beta. And when one electron is determined to be alpha, then the other must be beta. If one electron is determined to be beta, the other is alpha. But before that, we have to say we know both electrons are both alpha and beta. Again, a systematic way of constructing an anti-symmetric wave function of two electrons in the helium atom is to use a determinant. We have a 2 by 2 determinant. We have 1 over the square root of 2 factorial as the normalization factor. Inside, we have electron 1 in the first row, electron 2 in the second row. Wave function phi 1 in the first column, wave function phi 2 in the second column. And then we can expand this 2 by 2 determinant. We get 1 over the square root of 2 and squared, and then there's 2 exponential functions. And this part is the spatial part of the wave function. The spatial part is symmetric. Now we have the spin part, which comes from alpha 1 times beta 2 minus beta 1 times alpha 2. And this spin part is anti-symmetric. We can easily prove this entire wave function is anti-symmetric under the exchange of the two electrons. We simply look at psi of 2 and 1 versus psi of 1 and 2. So over here, we need to replace every one with 2 every 2 with 1 from this equation. So R1 becomes R2, R2 becomes R1. Alpha 1 becomes alpha 2, beta 2 becomes beta 1, etc. Now we can see this part remains unchanged. The spin part, well, changes sign. So we proved that this wave function is anti-symmetric. In general, the wave function of a many electron system is often expressed as the product of a spatial function and a spin function. Or we can say the spatial part or the spin part of the wave function. When the spatial part is symmetric, the spin part must be antisymmetric. When the spatial part is antisymmetric, the spin part must be symmetric. This is to ensure the total wave function as a product of the spin part and spatial part is antisymmetric. And in the end, we need to apply with quantum mechanical postulate 6. The wave function of the electrons must change sign under the exchange of any two electrons. Again, one systematic way of building an antisymmetric wave function is to use a determinant. And this is because when we switch 2 rows of the determinant, the sign of the determinant will change. Again, why do we choose the determinantal form when constructing the wave function of a many electron system? The reason is simple. Mathematically, the value of a determinant changes sign under the exchange of any 2 columns or any 2 rows. So if you look at this determinant and this determinant, I simply exchanged this row with this row. I switched 2 rows, and therefore the sign changes. And psi 1, 2 is negative psi 2, 1. When we have a 3 electron system, again we use a 3 by 3 determinant. Well, over here we have electron 1, electron 2, electron 3. In the 3 rows, we have phi 1, phi 2, and phi 3 in the 3 columns. Make sure phi 1, phi 2, and phi 3 are different from each other. Phi 1, phi 2, phi 3 should all be normalized. And also phi 1, phi 2, phi 3 are orthogonal to each other. And then we have a legitimate wave function for a 3 electron system. 1 over the square root of 3 factorial is the normalization factor. Just because if you expand this, we get 3 factorial terms. And then we need to ensure the squared modulus of psi has a integral value of 1. So that's why we need to have 1 over the square root of 3 factorial here. What if we have 100 electrons in an atom? Well, in that case, we need to write out a 100 by 100 determinant. We have 100 electrons labeled 1, 2, 3 all the way to 100, represented by 100 rows, and then we need 100 1 electron wave functions, phi 1, phi 2, phi 3, etc., all the way to phi 100. And then we write them out, phi 1, phi 2, phi 3, etc., to phi of 100. So that's why we have 100 rows for 100 electrons, 100 columns for 100 wave functions. And then you have a huge determinant, 100 by 100 determinant. When you expand it, you have 100 factorial terms. And that's why the normalization factor would become 1 over the square root of 100 factorial. So this is one reason why quantum mechanical calculations for even just one atom can be tedious and slow. Again, we have this many terms when we expand a 100 by 100 determinants. The Pauli exclusion principle results from the antisymmetric property of the wave function of electrons. No 2 electrons can have the same set of quantum numbers. In the helium atom, the 2 electrons in the 1s orbital have the same values of n, l, m sub l. They also have the same value of s, but they have different spin quantum numbers m sub s, plus minus 1/2. So the physical meaning of this is actually the z component of the electron spin. That can be plus 1/2 h bar or negative 1/2 h bar. If two electrons were allowed to occupy the same spatial orbital and have the same spin, then the wave function of these two electrons would be identical. Phi 1 will be equal to phi 2, and then we can just use phi to represent phi 1 and phi 2. Now if we write out the wave function for the two electrons, it becomes this. You have phi 1 in the first row, phi 2 in the second row. And you can see the first column is exactly the same as the second column. Now I'm going to switch these two columns, and I need to switch the sign. So after I switch the two columns, it's actually the same. So the determinant is equal to negative this determinant. So what happens here is psi 1 2 turns out is equal to negative psi 1 2. How can we solve this equation? Well, this has to be 0. Only 0 is equal to negative 0. That means the wave function must be 0, the probability density must be 0, the probability of finding two electrons with the same spatial and spin quantum numbers, well, is exactly 0. There's no way to have two electrons in the same atom with the same spatial quantum numbers and also the same spin quantum numbers. And therefore, in the helium atom, you must have one alpha electron and one beta electron. Alright, remember for all electrons, the value of s, this is for the three-dimensional spin, it's always 1/2. But the z component can be 1/2 or negative 1/2. So if you are looking at two electrons with the same spatial quantum number, that means if they have the same n, l, m sub l, well, they have to have different m sub s. One is half, the other electron is negative 1/2. And this is why each atomic orbital may accommodate up to 2 electrons, not 3 electrons. When you have 3 electrons in the same atomic orbital, inevitably you will have either 2 alpha electrons or 2 beta electrons. That will make this wave function 0. And that means the probability of finding 3 electrons in the same atomic orbital is 0. 2 electrons in different atoms may have the same set of quantum numbers just because their spatial orbitals have different centers. For example, if you have a diatomic molecule, let's say chlorine 2, well, it's possible to have a 1s alpha electron in the left chlorine and also 1s alpha electron in the right chlorine atom. That's possible.